Today, we are looking at a literally jaw-dropping new scientific breakthrough coming straight out of Kyushu University in Japan and Johannes Gutenberg University in Germany. It's a discovery that absolutely challenges everything we thought we knew about renewable energy and, well, how we actually capture it. Shattering the solar limit, the 130% paradox. Okay, let's dive right into this, because the very premise of this explainer sounds like a massive paradox, doesn't it? 130% energy output. I mean, how can a solar panel possibly produce more energy than it absorbs? It sounds like pure science fiction. But, the researchers behind this study have actually unlocked a way to shatter what we thought were the absolute physical limits of solar technology.
To really understand the magnitude of this, we first have to introduce the villain of our story. 33%. This is known as the Shockley-Queisser limit, and for decades, it has been this stubborn, deeply frustrating theoretical maximum efficiency that completely traps standard photovoltaic panels. Under normal circumstances, no matter how perfect the manufacturing is, you just can't convert more than a third of the incoming solar energy into electricity using today's classic panels. Just a third.
Think about what that actually means for your daily life. Most of the sun's energy never powers your laptop. It's lost as heat. A massive chunk of the solar spectrum beaming down onto an array goes completely to waste before it ever reaches your devices. The panels literally just sit there baking, unable to translate the vast majority of that broadband energy into anything useful, just bleeding it all off as heat. And this brilliantly illustrates the core problem. The sun bombards us with a really wide spectrum of photons. On one end, you have these low-energy infrared photons. They simply lack the oomph to knock electrons into action across the standard silicon bandgap, so they pass right on through. Then, on the flip side, you've got high-energy blue photons. These guys are bursting with power, way too much energy actually, but standard cells can only harvest a very specific fraction of it. So the remaining energy is entirely squandered, basically just thermalizing and bleeding away as excess heat. This is the wall classical physics hit. We were totally stuck, because escaping this 33% limit isn't just a matter of building clearer glass or a slightly cleaner silicon wafer. To actually break free, the researchers realized they had to leave classical physics completely behind and step into the astonishing, rule-bending realm of quantum mechanics. Escaping the limit requires a quantum trick. Enter singlet fission. This is the quantum phenomenon that literally changes everything. So, in a nutshell, singlet fission allows solar cells to take those high-energy blue photons, the ones that normally just waste their excess energy as heat, and do something incredible with them. It splits their energy into two smaller, perfectly usable excitations. Put another way, a single high-energy blue photon comes in, but it births two packets of energy instead of just one. And these energy packets, they're known in the business as excitons. But of course, every good scientific detective story has a complication, right? Well, here is the snag. Excitons have a frustratingly short lifespan and pretty much just vanish into the ether. While creating two excitons from one photon sounds totally perfect on paper, historically, this energetic split has hit a massive wall. They exist for just a tiny, tiny fraction of a moment, meaning they vanish long before we can successfully harness them into an electric current. It's kind of like catching lightning in a bottle, only to have the bottle instantly evaporate in your hands. So how on earth do you catch something that vanishes almost instantly? Well, you build an ultra-fast trap. And this is exactly where the team from Kyushu and Johannes Gutenberg Universities introduced their brilliant twist. They created what you could call a speedy capture team right at the molecular level. First, they used tetrazine, which is an organic molecule really renowned for its singlet fission skills. And then they paired it with molybdenum, a very specific metal complex that acts as a spin flip emitter. Let's move to and see how this builds into a functioning system, because it basically operates like a perfectly timed three-step quantum tag team. Step 1, the tetrazine molecule gets hit by the blue photon and splits it, performing that absolutely crucial singlet fission. Then, step 2, the molybdenum complex instantly jumps into action. Acting as the ultimate ultra-fast trap, it grabs hold of those excitons almost instantaneously. And finally, step 3, because of that lightning-fast capture, the energy is successfully secured before it has any chance to dissipate. The excitons are saved, and the energy is ready to become electric current. Now, before we get entirely carried away here, we do have to look at the fine print. Physics still applies. Sorry. We aren't magically creating free energy out of thin air, and your solar panels aren't going to somehow output more total energy than the sun is actually beaming down at them. What this whole 130% concept really means is efficiency in conversion. We are taking a single photon of light and successfully generating multiple energy states from it. We're finally utilizing the energy that was previously just thrown away as useless heat.
So the crucial point is the real-world application of all this. By mastering singlet fission and finally solving that really tricky exciton trap problem using molybdenum, these researchers aren't just doing some cool lab trick. As they put it, they are paving the way for much, much more efficient solar cells in the very near future. They are fundamentally breaking that 33% efficiency barrier that has totally bottlenecked the solar industry for decades. Which brings us to the ultimate takeaway. Think about it. When a single ray of sunlight can be manipulated at the quantum level to give us double the usable power packets, the implications are just staggering. We could generate vastly more electricity from the exact same footprint of solar panels. So I want to leave you with this question to ponder. When every ray of sunlight gives us double the power, how will this leap in efficiency reshape our cities and our energy future? It's an incredible thought, isn't it?